Hello everyone, and welcome back to Statics and Strength of Materials. This time we're in Chapter 5. We're going to learn how to analyze some trusses. Okay, analyze some trusses. First off, what are trusses? Well, they're these things. They're a structural framework and it has a bunch of straight individual members. Usually triangles. Triangles, a whole lot of triangles. In fact, a single triangle is called a simple truss. Now all members of this truss lie in the same plane, which is great for us. It's a set of coplanar forces, and we know how to solve that. They form triangles, like I said. And all members are two force members, which means that I don't ever have some sort of beam with a force applied to the middle. No, the forces are only ever applied to the ends of our object. And so these forces that they're subjected to are equal, opposite, and collinear. Now, why do we care about ceilings? We're trying to build giant buildings, but in the end, huge, absolutely massive objects are made out of trusses. These triangles can be built up into, bridges. They can build up to the Eiffel Tower. All those things are made using trusses. And so you have to know what the forces are within each individual member so it doesn't lead to failure. Now, there's a bunch of common truss designs right here. And for this class, we're not going to talk about the benefits or drawbacks of any of them. The biggest thing to remember is that they all are triangles. You can see that. Even if you look and you see a sort of trapezoidal shape, well, that is made of two triangles. Same here. Simply triangles. And so you might be realizing now why we cared so much about all those right triangles and oblique triangles from before in the law of cosine and law of sines. We were doing that just so that when we get to problems with these kinds of trusses, we'd be able to easily solve them by breaking them up into a series of triangles. Now, one important thing about all trusses, and the reason we have them all as triangles, is that it is a very simple but rigid and stable framework. For example, if you look at this particular guy over here, it's a square, and if we apply a force, well, this is not stable. Not just because of how the connections are, all these are going to have to resist a moment, which a lot of joints aren't really good for. This one does not have to resist a moment because it's got something pulling it down here and maybe pushing up on it here to keep it in equilibrium. This doesn't have that. So because of that issue, that is why we would want to have, we're going through the middle here, turning it into a nice set of two trusses. Okay, so let's talk about some truss terminology. So if we look at our truss, we see that we have the triangle and the circle. You've seen those before, and you're going to see them a lot again. And those are consistent. If you see a triangle in a picture, it is a pinned support. If you see a circle, it is a roller support. We then have the upper chord, which is this top line, and the lower chord, which is this bottom line. We have the web members, which are either vertical or diagonal. We have panel points right here at the top. And that's pretty much all you need to know. But biggest thing for all this, and span length. The full length right here is the span. Now, please remember, triangle, pin support, circle, roller support. Triangle, pin, circle, roller. So with that, we've been introduced to trusses, and next time we'll begin moving our way towards learning how to solve for all the internal forces in these trusses. Thanks for watching. I'll see you all next time. Bye-bye.